Basically, today I'm going to present on performance-based engineering scenarios in Singapore. Singapore we're a bit unique because, well, we're a pretty small country, about 712 square meters, with a pretty large population density. So our past scenarios, or rather the issues that require performance-based engineering, is a little unique compared to what you have in the rest of the world. Similarities would possibly be very dense cities with scarcity of land. Over the past 10 years, there's been a lot of need for performance-based engineering, mainly because of non-compliance in the code. This is one particular example. Basically, a facility like this, of this size, requires engineered smoke control. But there are some requirements. For example, the smoke reservoir length can't exceed 60 meters. The size of the smoke reservoir cannot exceed 2,000 or 2,600 square meters. So, like a facility like this, for this one, it's about 20,000 square meters. So basically, you need to break up the entire reservoir, smoke reservoir, into 20 zones. So it can give a lot of operational technical issues. So stuff like this, they go for performance-based, and basically you consider a design fire, and you ensure that the smoke layer height is maintained at a tenable level for the period of evacuation. Another scenario that we usually work on is these kind of bare steel structural constructions where they are interested to see whether, I mean, like for this case, the fire is adjacent to this column would likely fail. But what we want to study is does it affect the other steel columns enough to cause a catastrophic failure of the structure. So again, it goes for performance-based evaluation. And this one is a very unique problem. Probably you only find it in Singapore. This is a petrol station. You've got petrol companies coming in and they lease out the land to run their petrol station. But there is a criteria on basically using Margaret's law and all the setback distance. There is a criteria for what the setback distance should be for the adjacent property away from the roof line. And usually, in order to achieve, or rather to comply to the code, you need to actually, you will end up with only maybe two petrol dispensers for the whole development. That is hardly enough for the petrol companies to get a return on investment. So we do performance-based studies to see if, although this configuration is maintained, whether the radiative heat flux on the adjacent property is maintained within a tenable condition. So again, performance-based. The next one, which I mean, this is the crux of the whole presentation. There are a lot of old buildings in Singapore, 30 years old. So developers come in, they take over it, they want to spruce it up, make it in line with our more sophisticated society or changes in consumer requirements. So there is a case where there is always a change in use. For this particular development, there are basically two it's a below grade parking, two levels below grade and 4 levels above grade. So what's happening is the basement levels was initially designed for parking facility. So the requirement on the density of occupancy is much lower. And nowadays, in all the developments, they're converting the basement levels not to parking, but rather to retail, restaurants, F&B. The reasons why they do that is because the basement levels are usually connected to the underground rail system, and there's a lot of human traffic passing through the basement levels, so it doesn't make sense to leave it as a car park. So they want to change it to a retail or F&B facility to optimize their profits, basically. This is some example of change in use. For example, for this development, the basement 1, floor area of about 26, no, basically what they want to do is they want to have a retail of about 2,600 square meters, F&B of about 1,900, and supermarket space of about 1,700. So when you put in the occupant density for each of these, you end up with a figure of about 2,820 people for the basement 1 and 2,417 for basement 2. And with the existing escape provisions are as such. There's about a unit width of about 12.5 and for basement 1 and 11.5 for basement 2. So you end up with a permitted occupant load of only 750 for basement 1 and 690 for basement 2. So you compare that with the desired occupant load by the architect. So basically when the architects came to us with this issue, the alarm bells start to go off in my head, because we do a lot of performance-based, but when you talk about insufficient escape capacity or insufficient egress provisions, I get really worried, because in history we have seen so many fire incidents where people lose their lives because of insufficient escape provisions. I mean, one classic example is the station nightclub fire, which is very close to home for you guys. Where one of the main reasons for loss of life was overcrowding. But they were pretty desperate, so after much persuasion, we decided to give it a shot to see what we can do. So we took up a performance-based approach to actually try and study this and see whether life safety can still be maintained. But the very first thing we had to do, like for any performance-based project, is to manage the stakeholder expectations. We had to make it really clear to them that whatever they desire is a bit too much. So anyway, I'll touch on that a bit later. But coming to the goals and objectives, pretty much straightforward, just to safeguard all the occupants, safeguard the firefighters. And we add in another thing, because for this development, they were unable to actually provide more stair cores in the basement levels, because there are a lot of tunnels, MRT tunnels, train tunnels, road tunnels running underneath, and they could not do much piling, and micro piling was just not possible for this case also. So the performance criteria, Singapore Fire Code basically dictates that the visibility should be greater than 10 meters at 2.5 meters above the finished floor level. At 2.5 above finished floor, the temperature of the smoke layer should not exceed 100 degrees C. And of course, the available safe egress time must be at least 1.5 times that of the required safe egress time. So we came up with 5 scenarios. This is a model of the basement 2. Using DTECT, we basically, for a fast T-square fire, we ended up with a size of about 1.13 megawatts. So that was used as the design fire at the most remote location. A lot of causes or possible causes of the fire was postulated. Electrical fault, unattended cooking, flammable stores, discarded cigarette butts, arson attacks. So we kind of narrowed it down to either electrical fault or some unattended cooking. And the material was conservatively taken as a polyurethane. So some of the fire and life safety strategies that we put in place, or we dictated to be in place, firstly, the detection notification system by the smoke detectors, suppression systems, sprinklers, evacuation control. We dictated that there should be this dedicated staff to aid in evacuation at various locations in the basement levels. Compartmentation of all storerooms and other rooms containing hazardous material. Staircase pressurization, lobby pressurization, engineer smoke control for the entire mall, enforcement of a no smoking rule, and of course we dictated that no restaurants should be serving alcohol in either of the basements. So this is kind of similar to what Richard was going through yesterday. We could not use the escalators for escape, nor do we want to do it because the step height for the escalators are high, and that would be difficult for people to walk up during an emergency. So we decided to put in travelators with a very gentle gradient, only about 12 degrees, as opposed to escalator having a gradient of about 30 degrees. So people can very easily walk up without much difficulty. So, but the issue is this is internal, it's unprotected. So how are we going to prevent the smoke from actually coming into the escalator void, or the travelator void in this case, and causing evacuation issues? So we had smoke curtains. Basically, if there's a fire, smoke detectors will immediately activate your smoke curtains, which will drop and shield off the smoke from actually entraining into the escalator void. So using the BRE 186 and 258, we came up with the exhaust requirements for that level. So worked out to be about, for a fire size, we assumed a fire size of about 5 megawatts, and ended up with a extraction rate of at least 18 kg per second. So these you see here are the extract ducts. So what happens is this is basement 2, this is basement 1, there's fire in basement 2, smoke comes out, smoke curtains drop, smoke is prevented from going up, and over here, full drop curtains all the way to the floor. So this acts as a smoke reservoir. The smoke rises in and is extracted by the duct, and it comes out while maintaining a clear height of about 2.5 meters. But like I said, before we actually did anything, we had to manage the expectations of the stakeholders. So what you see here, this table here, this one shows the provided occupant load for B1 and B2. So we call this 100% provision. And we did an evacuation model for this. And then we increased it to 110%, 10% increase on each model for this, for 130%, 140%, 250%, and finally the desired occupant load of 376%. Don't know if so even the people in level 1, this is basement 2, basement 1, and level 1. Even the people in level 1, the maximum occupant load in level 1 was simulated to because we didn't want to discount any interference to the evacuees from the bottom 2 levels due to the people in level 1. So these were all taken into account. Okay, and the findings were as such. This one is just the movement time. We're not considering the pre-movement time or the alarm activation time. So what we're actually trying to do here is, like we have been through so many evacuation presentations, and everyone has a common consensus that pre-movement time is going to be very, very difficult to actually approximate. So the assumption, right or wrong, I mean, we can discuss this later, but that whatever code provisions or code requirements, or whatever is stipulated in the code, ensures life safety. So based on that assumption, what we're trying to do here is we are going to compare movement time with code stipulation against what we desire to achieve, or rather the non-compliance. So in this case, the movement time of a provisional occupant load, what the code stipulates, without the use of a travelator, works up to about 300 seconds. And as we work down, 110%, 130%, it starts to increase. Now, with the travelator provision, you realize when we come to 140%, there is the same movement time that is achieved. So in other words, based on the assumption that the code stipulation ensures life safety, we can pretty much say with a certain degree of confidence that 140% of the provision occupant load will still ensure life safety because the same movement time is achieved. And we assume that the same pre-movement time will be there as well. So, of course, this was proposed to the client, but they were still very unhappy. But anyways, we went ahead with our performance-based study. Yeah, this is just a graph to show what I demonstrated just now. We started working out on the required safe egress time, so putting in alarm activation time, which we determined from detect, pre-movement time, which we took from data by Fahy and Prolux, and we came up with a required safe egress time as follows. So 500 seconds for the what is stipulated in the code, and up to 936 seconds for what is desired. Went ahead with the CFD modeling, and basically what it shows is that the visibility at 2.5 meters above finished floor after 20 minutes of the start of the fire is pretty much maintained at within tenability limits. And you can see there is over here, I don't know if you can see, but it shows that there is no smoke spilling into the travelator void. So that's a good sign. Same thing is seen with the temperature. There is no smoke that is spilling into the travelator void, and generally the area of basement 2 is maintained below the 100-degree requirement. So we can say that the available safe egress time, our simulation time was only for 20 minutes. So the available safe egress time is at least 20 minutes. So using that and capping it off at 20 minutes, compare that with the required safe egress time, to achieve a safety factor of at least 1.5, we can increase it to 250%. Okay, but this is just in theory, or rather whatever we have studied. But to be honest, I would be more comfortable with 140%, as I illustrated with the evacuation modeling. We're trying to find some middle ground. But like I said, what our recommendations would be 140%. So we're trying to convince everyone else not to push it any further, because coming to lack of egress provisions, I think it's quite a serious issue. So anyway, the whole idea of this presentation was we are just comparing the movement time, and we are assuming that the code stipulations ensure life safety, and we have some non-compliance, and we are just running the evacuation model just to take into account the movement time only, nothing else. So comparing that, we're trying to see how far we can push the limit so that we can achieve the same evacuation time as stipulated in the code. So that's. But there are some issues which we need to take into account, critical design issues, which will cause the whole design to fail. For one, all the fire life safety strategies that I discussed just now must be implemented. And the other thing, the area surrounding the travelator should be clear of all combustibles and obstructions at all times. And any shop facades, no shop opening should be at the entrance of the travelator. Any shop facades, window panes, we're still studying it. We're still studying the architectural designs, but we would recommend even as far as putting fire shutters to screen off any potential radiation of fires from the shop units that might affect people trying to access the travelators. So basically, that's all I have. Can take some questions now.
Thank you. Do we have questions for Shyam? No? All right. Thank you again very much.